So I would like to introduce our speaker for the second sessions. Our first speaker, Dr. Osvaldo Espin Garcia. He's from Western University at the Department of Epidemiology and Biostatistics. And he did his PhD in Dalanana School of Public Health at U of T. And his research focusing on the statistical machine learning, computational methods for statistical genetics and genetic epidemiology and deep phenotyping complex traits such as cancer, Crohn's disease, and osteoarthritis. Our second speaker, Kevin Grant, you are from University of Windsor, the Department of Math and Stat. You get a degree from Waterloo. We are alumni. Oh, I forgot to introduce myself, but let me get this done first. And you got your degree, PhD from Statistics at University of Waterloo, and then you spent 2.5 years as a postdoc associate at the Western University. And your research areas include wildland fire science, spatial interpolations, and curing theory operation research, as well as their intersections. And the first speaker, oh yes, Dr. Pravipa Janganathan. Yeah, it's a bit difficult for me. And she's from a master university in the Department of Math and Stat. And she also served as an associate member of the School of Computer Science and Engineering. And before she joined the master, she was a postdoc at the Stanford University from 2016 and 2020, working with Suzanne Holmes, right? Our speaker of today's DLSS. And so lastly is Brian Ling. You're from Queen University, Department of Math and Stat. And your research interest is in the shape constraint inference, survival analysis, bias sampling, and nonparametric tests. You got your PhD from, Columbia University, right? Okay, so I forgot to introduce myself. My name is Zeny Feng. I'm a professor in statistics from University of Guelph. Okay, so let's turn to our first speaker.
Thank you. Thanks, first of all, to the organizers for inviting me to this talk. So I leave the title there. I put a subtitle just to temper a bit of the expectations. The entire talk won't be about like giving advice for launching a career, but anyway, so I'm just talking a little bit about my experience and how this applies maybe to other future statisticians or assistant professors or so on. So anyway, so for my experience, so there's maybe all or you are familiar, or most of you are familiar, but essentially we have these 4 areas, with trainee recruitment, grant writing, or applying to grants or obtaining grants, more importantly, publishing and collaborations. Of course, there's many challenges on these topics. So for example, as an Erica researcher, so we have no brands, so we are essentially unknown people. So how do we approach that and how navigate that space? We have effectively very new skills on grant writing. We need to identify or being able to navigate all the different competitions available to us. And of course, we never done probably a budget before, so we need to put together a budget at some point, which of course may represent a challenge. The big motto, publish or perish, probably very familiar with all of you, so that's yet another challenge. And of course, in terms of collaboration, so we have a limited track record of collaboration, so the experience with collaboration. So how can we leverage this and how to make, circumvent these issues? But luckily, there's also opportunities as an ECR, mainly for essentially recruiting students. We are maybe easier to connect with them, easier to relate because we, technically we are younger, even at heart. Luckily, there's also ECR specific provisions for different competitions, which really aid and support initiating the grants applications. In some situations, in many institutions, have some protected time, which is always appreciated, to get some time to write those grants, gain some experience, and so on. And of course, the many opportunities that we should apply. So you probably heard some of you more than once. Lastly, so again, as an ECR, maybe we are more, easier to adopt technological tools, and I list a few of them. How to write more efficiently, how to manage the references more efficiently, how to be informed of the more recent trends, and so on, how to code more efficiently, and so on. So essentially this, and maybe lastly use maybe even ChatGPT and so on for inspiration perhaps, or any other things. Anyway, perhaps the main thing in situations is that for collaborations as an ECR, we're maybe luckily not alone. So we can partner with other ECRs, so we're on the same boat, so it's in our best interest to gain some attention, and in that regard, I've been lucky that the collaborations that I've been granting have led me to the field of osteoarthritis. And for those who do not know, osteoarthritis is this chronic joint condition that affects 1 in 7 Canadians in the last numbers that were done. So it's most commonly presented on the knee joints. I have this illustration on the right hand, essentially how the knee joint deteriorates under osteoarthritis. Unfortunately, there's no cure, nor approved disease-modifying drugs on this disease. And there's this complex etiology with genetic, epigenetic factors, and environmental factors involved. And more often is characterized, so if we want to characterize the progression of the disease, is either for a structural, which is basically denoted based on the structure of the knee, or the biology of the knee itself, but also symptomatic changes. So things like pain, function, how these evolve over time, and that's usually how this is one of the other characterizations. Okay, so that was my one slide on OA. Hopefully you're relatively familiar with it by now. So motivating data, and this is probably one of the main characteristics of a biostatistician, or as a biostatistician, I often get inspired by data. So whenever I see a data, I see, okay, what problems are not being solved out there, and maybe solve or address different methods to it. So I kind of like tailoring methods to my data, as opposed to maybe come up with a method and see what data set applies to this method, right? So that's kind of that's my own approach. Not necessarily better or worse, but anyway. So just in terms of motivating data, this osteoarthritis initiative is a very rich observational study, which about 5,000 participants, jointly sponsored by the NIH and pharmaceutical companies. The main idea is to prevent and treatment. Lots of data, lots of demographic, imaging, biospecimen, accelerometer data even, so you really name it. So there's mainly 3 subcohorts which tend to study different aspects of the disease. So the progression cohort tends to focus on people who already had the disease at baseline and sort of monitor, evolve over time. Incidence, people who are at risk of developing the disease, to sort of a little bit to enrich that cohort, and essentially, hopefully, or maybe not so much, when this person is going to develop the disease, and then like a very small proportion of controls, just to see, be able to compare perhaps. Okay, so that's kind of the motivating data that essentially spawns, or is essentially spawning my research program. So, and I'm going to briefly talk about 3 projects. The first project is a latent class linear mixed effects model for monotonic continuous process measured with error. And I thank the previous speaker for talking about latent class, which really lays out the ground for this talk, or this portion of the talk. So what about these latent class mixed models? So specifically in the field of osteoarthritis, so we use, or people use X-rays to monitor, both diagnose and monitor the disease. There are different features that radiologists would look at, or clinicians would look at. Like so one of them is the joint space width, so essentially the space between the 2 bones that form the joint, and especially how they narrow over time. Essentially, is a characteristic, or will capture progression, and this relates back to this idea of the structural changes. As I said, there's no available treatment. So that means that potentially, thinking of there's a sustained or a monotonic chronic deterioration over time, and we're going to leverage this fact for the model that we're proposing. And there are many different sources of potentially measurement error in this joint space narrowing. The diagnostician, so if you show the same X-ray to 2 different diagnosticians, there may be some variation in how they actually measured, but other things could contribute to this measurement error, such as the machine that's being used, even the joint angle, the positioning, even though the best efforts are to put the knees of all participants in the same position, there's slight variability that could influence this measurement. And the main objective of this project is really to identify these trajectory curves based on these reported medial minimum joint space width and available risk factors. So just to have an overview of the model formulation that we use, or that we're proposing. So these main 3 components. The first component, essentially assuming that there is underlying this latent class that will capture this heterogeneous population. And we assume that this can be modeled through a multinomial regression model informed by this pi, and that pi can depend on certain covariates of interest that will assign or help us assign people to different classes. And then the second part is assuming that there's this W variable, which is a latent error-free monotonic response. And essentially, the key assumption is that we're assuming that as time evolves, that latent variable has a monotonic pattern. In this case, for the OA application, we have like a non-increasing pattern, right? So the joint space narrowing will be either staying the same or decreasing over time without any appropriate intervention, which unfortunately there aren't one. And we are relating that to a set of exogenous covariates, which I'm denoting by X, Z, and U by this linear predictor, which is a composition over all fixed effects, relative effects, and class-specific fixed effects. And the main assumption is given here on these equations over here. So at time 1, we assume that the initial latent variables follows a normal distribution, but any subsequent times assuming a truncated normal distribution. And then the last part, to account for the error measurement, we assume like a very classical additive measurement error, where the observed variable, which I'm denoting here by Y star, is going to be this latent class plus some error, which I'm assuming that is normally distributed with case or class-specific variance. Okay, so that's the model. I'm not going to go into the detail due to the time constraint, but we essentially using a very standard Bayesian inference with conditionally conjugate priors, using MCMC, using JAX, which admittedly is quite fairly slow to converge, but it does. But it presented some challenges, mainly on the problem with identifiability, and this is a well-known phenomenon in latent class models or in clustering or in related fields. So whenever there's mixtures, there's this issue of identifiability, which we attempt to solve it using this label switching package, kind of like a two-step process. And we compare against like a standard latent class linear mixed model. And generally speaking, in our simulations, which again, I won't show for lack of time, essentially the proposed model shows some improvements as the model increases the sample size and there's an increased number of time points. So just to show you a little bit of the challenge that we're facing, so we have the trajectories here over time. So here the time in years, and on the y-axis we have this joint space width or total joint space width. Essentially the sum of the joint space width across both joints in a single person. And you see that there's this kind of like a trend towards getting down as you would expect, but some of them kind of go up and down as you can see in some of them. So the idea is that we try to identify clusters in these kind of messy data. Okay, so just an overview of the results. For label switching, we use this equivalent class representatives algorithm, and we identify the best number of classes, which turned out to be 3, which is illustrated here using the WAC and the LLO. And the inference was based on 30 MCMC iterations. So as you can see here, the main feature, something that we like about this model is that as opposed to the standard one, which seems to be solely dependent on the intercept, so our approach was able to roughly start at the same point, which is what you would expect, and then through the latent class characterization, see which of the trajectories will be a more of a decreasing trend or maybe more of a stable trend, which has implications on maybe how we're going to approach or how maybe people will be follow up and so on. Okay, so that's the first project. The second project uses a co-registration method to quantify physical activity levels. And this is also, mainly motivated by the fact that physical activity is believed to be beneficial for OA, but self-reported information may be subject to biases such as desirability, social desirability, or recall biases. So instead, we rely on wearable devices. So the idea is that we want to use these co-registration methods to improve comparability of accelerometer measured physical activity data. And just a very quick overview of the methods. I won't read these to the interest of time, but the idea is that we have these sort of curves measured through the accelerometers, in order to make the curves more comparable. And people have different, essentially, starting times where they start their day or where they end the day and so on. We want to sort of align them to a kind of population trend, if you will, through the use of these warp functions, such that we come to this register time where we can make the people more comparable, and so on. So that's kind of, we use this idea in the data that we had. Here I'm just showing the 48 visit where we had accelerometer data available. We came from this data from the OAI and came up to convert this to the register time. And then from the model that we fitted under curve registration, we're able to obtain these predicted curves. And then for each of those predicted curves was more easier to calculate what we define as area under the register curve, and then as a measurement of the physical activity levels. And then with that physical activity level new data, so we're trying to essentially see are there any factors that associate with this area under the register curve. So the good thing is that this measurement of area of AURC actually captures expected patterns. So you see that males tend to be a bit more active than females. People with overweight tend to be less active than people with normal weight. So it seems to be capturing actual physical activity. However, we didn't see any associations with AURC and long-term OA outcomes as we would expect. We believe that this is the case because it's in this particular cohort, the OAI seems to be like a fairly inactive population. So that's maybe a reason why we're not seeing what we would expect. But anyway, so some ongoing works, we're looking at genetic loci and predicted gene expression levels that may be associated with this measurement of area under the register curve. So maybe with the remaining time, the third project, which is very much ongoing, we're developing this multivariate functional regression model for colocalization under a composite null hypothesis. And essentially, this builds on the increasing availability of multi-omic data at the individual level. And we want to sort of understand how orthotropic outcomes and microRNA levels can shed some light on some regulatory mechanisms. The main idea is to develop this multi-trait, multivariate colocalization approach with mixed distributions using individual level data. So maybe I'm just going to focus here on the, one more minute, how this works or how we're proposing. So for here, we are effectively using a scalar on function approach to model in a given loci. We're assuming there's a underlying function that operates for the SNPs. And then we want to identify this genetic effect function that associates back to an L number of traits, which is illustrated here on the second figure over here. And then we ultimately want to test whether the functions follow this null hypothesis. So whether the product of these two functions is equal to 0, which of course can be a result of either beta1 function being equal to 0, beta2 function being equal to 0, or both being equal to 0. Thus, it's a composite null hypothesis with this a bit of a requires further developments. So just very preliminary results and notes. So again, with the way we're estimating this Feng colloc uses this two-step procedure, using this expansion representation and a multivariate covariance generalized linear model for the regression part. It can accommodate both local and global locus level colocalization tests. So essentially what I mean by that is that we can test for this overall region or for kind of local specific regions that may be of more interest. And we're evaluating these null hypotheses under empirical approaches, mainly permutation and adaptive bootstrap approaches. We're showing some promising performance and so on. So in the future, we're going to start applying these to progression traits. Okay, just some conclusions. So the main bottom line is that finding good collaborators and motivated data can help in identifying some nice research areas. And I'm going to let you read that last part. Some ongoing work. So we're using some of these alternative data sources, so the raw images, for example, how to incorporate multiple traits to characterize the latent classes. And lastly, we want to integrate these data in a maybe more cost-efficient manner. Okay, so just want to acknowledge my trainees that work on these projects, my collaborators, and of course the funding that I currently hold. Okay, thank you.
Thank you, CANSSI, for the invitation. And the title of the talk is a nonparametric light equal ratio test for univariate shape constraint densities. This is our joint work with my collaborators, Gary Chen from University of Washington, Chanfa Tan from University of Texas at Dallas, and Philip Yang from the Chinese University of Hong Kong. So here is the outline of the talk. I will first introduce what is shape-constrained inference, especially focusing on density estimation problems. And then I will introduce our testing problems and our test statistics. Then I will move to talk about some asymptotic results of our proposed method, and followed by a bootstrap procedure to calibrate the critical values of the test. And then I will present some simulation studies and compare it with other possible tests in the literature. And then I will mention a simple application of our test. So basically, in shape-constrained inference, we are usually interested in estimating some functions. And these functions could be like the distribution function, density functions, hazard functions, or regression functions. And by shape constraint, we mean we impose some constraints on the shape of the function. So some common constraints are monotonicity, convexity, or log concavity. Okay? So this field has been receiving more attention due to some reasons. First, these constraints are sometimes direct consequence of the problem under investigation. For example, if you have current status data or interval censoring data, then you are trying to estimate the distribution function. It falls into this domain because of the non-standard asymptotic of the rate of convergence. And the other reason is we can think of shape-constrained model as in between a fully specified parametric model and a fully unspecified non-parametric model. But you try to retain some qualitative shape features. For example, like in isotonic regression, you impose the relationship between your covariate and response is monotonic, okay? Or in convex regression, you impose the relationship is convex. And another important feature about the shape-constrained estimator is the non-parametric maximum likelihood estimator or the least square estimator are often fully automatic compared with other non-parametric methods. Automatic in the sense there is no additional tuning parameter to be chosen. If you use a kernel method, you need to choose the bandwidth. If you use a smoothing spline, you need to choose the number of knocks and so on. Okay. So now let's talk about density estimation, which is our focus today. Our setting is we have a random sample x1 to xn. Then the likelihood is the usual likelihood is the product of the density derived at the samples. And here the script f is a shape-constrained class of densities. And it can be shown that for different classes, we do have a well-defined maximum. Okay? And the classes that we consider here are the class of decreasing densities, the class of k monotone densities. So in particular, one monotone is the same as decreasing density. So here, decreasing is, I use it as the same as non-increasing. So two monotone density is a density that is decreasing and convex. And for k greater than or equal to 3, you impose additional constraints on the derivatives. And a characterization for the k monotone density is it can be represented as a non-parametric mixture with the beta distribution. And we also consider the class of completely monotone density. It also has a characterization as a non-parametric mixture with the exponential distribution. So the G is not a discrete distribution. In general, can be any distribution. So some particular examples are just mixture of two exponential distributions will be a completely monotone density. And then another class of density that is well studied recently is the log concave density. So a density is log concave if the logarithm of the density is concave. So in particular, it is a subset of the class of unimodal density, and it contains many of the well-known parametric distributions like the normal distribution, exponential distribution, and so on. So it can be used as a non-parametric realization of these parametric distributions. So now let's talk about our main work here. So the setting is we have a random samples from some density f, which belongs to some non-parametric class of densities. Here, we aim to test whether this f belongs to some class, so script f0, or not. And we focus on the class of shape-constrained densities. For example, we can test if the density is decreasing versus it is not decreasing, whether it is log concave versus it is not log concave. And then This is our test statistics. So you can see it's a likelihood ratio and iterated at two different estimators. The first one in the numerator is the nonparametric MLE under the null hypothesis. So it is a well-defined object under the null hypothesis of the shape constraints. And then for the denominator, we define a type of a histogram type density estimator, which has some benefits, as you will see in a moment. So let me define the histogram estimator. So let's see to be the order statistics of the observed data. And here we want to define a piecewise constant density function, which is meaning like a histogram type. And here the nu is the number of data points that we use to form a group. So here you can see from the smallest one to nu plus 1 to 2 nu plus 1. So we have many intervals, and we define a constant function that is inversely proportional to the length. So to understand this, draw a simple figure for n equals 10 data, and nu equals 3. Then we combine 3 data. Other than the first one, we combine 4, and then combine 3. And then the height is inversely proportional to the length. Okay. And then let's talk about the asymptotic results and some properties of our proposed test. So here is our asymptotic node distribution. So the psi is a digamma function, psi1 is a trigamma function. And then for the classes I mentioned, the K-monotone, completely monotone, and log concave densities, we have the following theorem. So the nu, we call the nu is the number of samples I use in one interval. So I allow the nu to grow with n. So under some additional conditions, but these conditions are not imposed on the derivative of the true density, but only on the tail of the density. Okay, Tn is our test statistics. So we have some scaling constants sequence and some centering sequence and scaling constant sequence. Then the rate of convergence is n times nu, the square root of n times nu. The denominator, this sequence actually converges to a constant if nu goes to infinity. And these are also some constant sequence. So you can see a particular feature is the asymptotic distribution is distribution phi. It does not depend on any additional auxiliary parameter of our true density. So this is an important feature. Okay. Here is the main idea about this theorem. We can basically do a telescoping into two terms. So F0 is the true density. So then we study each term separately. The first term is the average log likelihood ratio iterated at the MLE and the true density. And we show that it converges quicker than the second term. So that means the asymptotic distribution depends on the second term. And then we can decompose the second term into two separate terms. I call it to be Mn and Rn. So F0 is the true CDF. It's a true CDF because we are talking about density estimation, so it is a continuous distribution. And the Z is the order statistics. So if you evaluate the order statistics at your F0, you get an ordered uniform. It's in the same distribution, right? So Mn is distribution phi. For any finite sample, is completely distribution phi. It does not depend on our true density. And Rn is some remainder term that converges quicker. So that means for equation 1, this expression, Mn is the dominating term. And then going back, we have to study the rate of convergence, which is a non-trivial task. Okay, so this ratio is the average log density iterated at the MLE and the true density. And the rate at which this goes to 0 under the null hypothesis depends on the class of density under consideration. In general, it depends on the size of your class that you are maximizing. Okay. So due to time, I will focus on the K-monotone density case, which includes the one monotone, the decreasing density. So here, the script K, FKB0A denote the class of K-monotone densities with supports contained in a compact interval and bound above by B. And then Gao and Wellner, they established an upper bound for the bracketing entropy for this class under the Hellinger distance. Okay, this equation 2 is the bracketing entropy bound. And if you use empirical process theory, you know if you obtain this kind of bracketing entropy bound, it is possible to obtain this kind of rate of convergence. And the K here is the K in the K monotone. So if you have a smoother function, you have a quicker convergence. Okay? But their result is a little bit restrictive because this band is only valid for that cast, which is bounded above by B and has a compass support, it has a bounded support. So we want to make our test more applicable. So we establish some additional results. So here the script Fk is the class of all K monotone densities without the additional boundedness or the compass support. And then the main observations is to observe that even if the true density does not have bounded support or is not bounded from above, the MLE for any finite sample is actually bounded for any finite sample. So we establish some results. Then we can apply the previous bracketing entropy result. Together we can derive some weight. The only thing is we have up to a logarithmic difference of our weight of convergence. So we can do some similar analysis for completed monotone. And for log concave density, Doss and Vella, they already established this kind of weight of convergence, so it's their work. And then under the alternative hypothesis, the consistency of the test rely on the fact that this ratio will be greater than some constant. So that's why when you multiply by the scaling factor, it will converge to infinity. Our test statistics will converge to infinity. So our test will be consistent. Although our test statistics, the asymptotic distribution is distribution free, but we find that if we use a bootstrap procedure, it will provide a better control of the type 1 error. So the procedure is pretty straightforward. It's like a standard bootstrap procedure. The only exception is we bootstrap from the MLE, which is under the null hypothesis. We can find the MLE and then we can simulate from the MLE instead of bootstrapping from the empirical distribution function. And we prove that this procedure is valid. Okay. So now I will briefly compare our test with other existing tests. So you will ask, a very natural test is an L2 test. Let's say you use the empirical CDF, say the decreasing density case. Fn hat is the least concave majorant, which you can think of as the MLE in terms of the distribution function. Then the L2 test is very natural, right? You can do it with dt or dFn. dFn is the empirical measure. And other lateral test is the supremum norm, so the supremum distance. But although they are very natural, establishing their asymptotic distribution usually requires more assumptions. In particular, in their paper, for the L2 test, they need to assume F0 is twice continuously differentiable, bounded away from zero, bounded from above, negative derivative is also bounded, and their asymptotic distribution also depends on the derivative F0 prime. So it requires additional estimation if you try to use their asymptotic distribution to find the critical values. So in other words, while they are very natural, establishing the asymptotic distribution requires you put additional assumptions that you may want to avoid. So in the simulation studies, these are some of the alternative distributions we considered. And then we compared with this test. And in many scenarios, our likelihood ratio test performs pretty well. Okay? And all the critical values are used using the bootstrap procedure, including the L2, L2 prime, and L infinity. Okay. And then lastly, for the log concave density, we consider these alternative distributions. The figures shows the log of the density. So if the function in the figure looks like a concave function, then it will be more difficult to differentiate the null hypothesis and the alternative hypothesis. So these are the beta distribution, log normal, and the mixture of two normals. And then we compared with the Chase test by Chen and Samoff and the split likelihood ratio test or the universal inference by these three authors. But their split likelihood ratio tests, their alternative make use of a kernel density estimator. At least they propose that one of them they use. But the kernel density estimator has a disadvantage that you need to do a boundary correction if your distribution is not bounded. Okay. Then the split 1, split 2, split 3, the difference are using which types of support information. The split 1 uses the true support information. The split 2 does not use any information, so it does not work well. The split 3 uses the data, like the minimum and the maximum as the support. And the trace test, although it looks powerful, but it sometimes cannot control the type 1 error very well. It's very inflated for these numbers. Okay. This is for different sample size. So lastly, we see a very simple example. So we consider the time intervals between explosions in mice that result in loss of 10 lives, so it's time data. So the original paper, they use an exponential distribution fit to this data. And then more recently, these two authors, they propose an extra parametric family to fit to this data. And then if we look at the histogram, it looks like it has a decreasing trend. But looking at the histogram is sometimes not very useful because the appearance depends on the beam width. So we apply our test to test if the null hypothesis that it is decreasing or not, and it does not reject the null hypothesis that it is decreasing. So that means it is plausible to use a nonparametric density estimator, like the granular estimator or its smooth version, to fit into this data instead of using a parametric model. So that's all for my talk. Any questions?